Now that we have some semblance of why we would use equivalent circuits, we need to know how to determine equivalent circuits. We've already looked at the simple case, a circuit that can be combined to a single source with a resistance using source transformation. Those circuits are rare. A more general approach is required for this to be useful in the general case. There are three parameters of interest to us: a source voltage or current, and a source resistance. We can proceed by looking at an equivalent circuit and seeing what we can figure out from it. Here's an example of an equivalent voltage source. If we assume that this voltage source has the same properties as the circuit it's equivalent to, one property we could look at would be the voltage at the output terminals. Since there is nothing connected out there, I will call this V open circuit. Since it is an open circuit, no current flows through the 240 ohm resistor. So if we did a KVL loop, we would find that the open circuit voltage is 48 volts. If we were to put a wire at the output, we could determine the maximum current the circuit can supply. This might tell us something else about the source. The current in this case can be determined simply by using Ohm's law. We would find that the current is the voltage source divided by the resistance. This equivalent circuit has an open circuit voltage at the terminals of 48 volts and a short circuit current at the terminals of 0.2 amps. And if we look at the ratio of the open circuit voltage to the short circuit current, we would get the equivalent resistance of the source. Furthermore, we know from previous videos that this source could be represented as a current source in parallel with a resistance where the current happens to be the short circuit current. Not only do we have two representations for an equivalent source, we analyze this a little further, we'll have much more general information. If we look at the equivalent voltage source and attach an arbitrary load resistor, we could analyze the current through that load resistor or the voltage across the load resistor by looking at the extreme values. The smallest load resistance possible would be 0 ohms. In this case, the voltage across the load is 0 volts and the current through the load is at its maximum value of I short circuit or 0.2 amps. The largest load possible is an infinite resistance or an open circuit. In this case, the load current is 0 and the load voltage is the open circuit voltage. This is a linear circuit and the voltages and currents will all fall on a line between these two values. This line is called the load line because it represents the current voltage relationship for any value of load resistor that can be attached to a circuit. The slope of this line will be -1 over the resistance of the source. The circuit we just looked at was as simple gets, but the principle applies to any linear circuit. If we want to know the output of a linear circuit for any possible load resistor, a similar load line can be generated, as long as we know 2 points. The easiest points are the open circuit voltage and the short circuit current. Let's look at this now familiar circuit. If you remember from the last video, we used a source transformation to change this circuit into the following equivalent circuit. This time, instead of using source transformations, let's see how the open circuit voltage and short circuit current can be used. The open circuit voltage is the voltage at the output terminals with nothing connected. To determine the open circuit voltage, let's begin by identifying it. If nothing is connected, there can be no current through the 10 ohm resistor. If there is no current through the 10 ohm resistor, there is no voltage drop across it. That means by Kirchhoff's voltage law that the voltage across the 40 ohm resistor must also be the open circuit. Looking at the circuit, the open circuit voltage can be determined using a single node equation. Remember that the open circuit voltage will be the potential across the 40 ohm resistor. Let's start by selecting a reference node. Since the 15 volt source is connected to the reference node, this node is at 15 volts. The open circuit voltage is across the 40 ohm resistor, so this is the node voltage. We can then pick directions for our currents. Then we can write following node equation. If we multiply through the equation by 120 ohms, we get this. Combining the terms, we solve for the open circuit voltage equal to 5 volts. Now let's determine the short circuit current. To do this, we'll short the terminals at the right side of the circuit. Don't do this in real life. Short circuits often lead to fires. Short circuit current will be the current we get through the wire. Even though we were looking for a current, I'm going to solve this circuit using node voltage analysis because it requires only one node equation. I'll start by selecting a convenient reference node. Then, because of the 15 volt source, this node is at 15 volts. Let's call the remaining node Vx. After choosing directions for the currents, we can write the following node equation. Multiplying through by 120 ohms, we get this. Combining terms and solving, we get 1.67 volts. The current can then be written as Vx minus 0 divided by 10 ohms, resulting in a short circuit current of 0.167 amps. So we have an open circuit voltage of 5 volts and a short circuit current of 0.167 amps. We take the ratio of these two values, we get a resistance of 30 ohms. Using these values, we get the following equivalent circuit, which is the same exact result we got by doing source transformations. We use the short circuit current and the resistance, we get the source transform of the voltage source. These circuits do have names. The voltage source in series with the resistor is called the Thevenin equivalent circuit. The current source in parallel with the resistor is called the Norton equivalent circuit. Although, I don't know why I said Norton quietly. People are more afraid of Thevenin. One more observation about this circuit. The source in the circuit is an independent voltage source. If we turn the voltage source off, remember that turning a voltage source off results in 0 volts. We have only resistances left in the circuit. We can then combine the resistors. Let's highlight these nodes for clarity. Then we can easily see that the 3 resistors are in parallel and can be combined by adding their conductances. The result is an equivalent resistance of 20 ohms. 20 ohm resistor then can combine with the 10 ohm resistor, resulting in 30 ohms. Once again, this is a surefire way to determine an equivalent circuit. We simply take the circuit, find the open circuit voltage, then determine the short circuit current. The equivalent resistance will be the ratio of the open circuit voltage to the short circuit current, and this will work every time. However, we can see from the resistance calculation at the end, there was a quicker way to determine the equivalent resistance in this case. Since we have 3 parameters we are interested in, the open circuit voltage, the short circuit current, and the equivalent resistance, and those things are related by Ohm's law, we need to only find 2 of them to determine the values for all 3. Even though using the open circuit voltage and short circuit current will always work, sometimes it's more efficient to simply turn off the independent sources and combine the resistors. There, I said it again, turn off the independent sources to determine the resistance. What if the circuit has dependent sources? Determining the open circuit voltage and short circuit current will still work for finding 2 of the 3 parameters possible to fully specify an equivalent circuit. Obviously, however, we cannot combine a dependent source with a resistor. You know that's not how you're supposed to use that. You're gonna wind up hurting somebody or staining something. Alright, let's look at a circuit with a dependent source. If we want to find an equivalent circuit for this circuit, the open circuit voltage and short circuit current method will work. Let's begin with the open circuit voltage. Since we're looking for a voltage, let's choose to do node voltage analysis here. We'll start by selecting a reference node. Then this node is at 2 volts, this node is VI, and both of these nodes are at the open circuit voltage because no current can flow through the 2 kilo ohm resistor. We went over why a few minutes ago. After assigning directions for each of the currents, we can write the node equation at the first node with the current entering equaling the currents that leave. The other node only has the current through the 12 kilo ohm resistor and the dependent source. These 2 equations can then be simplified by multiplying through them by 12 kilo ohms. Then we can gather terms to simplify them further. And finally we have that the open circuit voltage is negative 23.45 volts. We can then put a wire at the output and determine the short circuit current. Since we're looking for current in this case, let's choose mesh currents analysis. We'll begin by assigning 3 mesh currents. Then choosing a direction for each of the voltages, we can start by writing the equation for the left-hand loop. Loop 2 contains a current source, so we cannot write an equation for just loop 2. We can, however, do a loop around the outside of both of the right-hand loops. We get a second equation from these loops by writing the current source in terms of mesh current. The final thing we have to do to complete our system of equations is to write the controlling parameter in terms of mesh currents. With 4 equations and 4 unknowns, it is probably most efficient to use a matrix to solve the system. So let's reorganize each of the equations into something that goes more easily into a matrix. These solutions come from matrices I prepared earlier. The answer we're interested in here is the short circuit current of negative 10.30 milliamps. So with an open circuit voltage of 23.45 volts and a short circuit current of negative 10.3 milliamps, we can calculate the equivalent resistance of the circuit at 2277 ohms. So we have the Thevenin equivalent of the circuit on the left and the Norton equivalent of the circuit on the right. But if we wanted to find the resistance of the circuit directly, to do that we would employ a technique similar to that which resistance meters use. If we remember way back to the beginning, the definition of resistance is a ratio of electric potential to current. So if we want to know a resistance, we can apply a test source and see what the response of the circuit is. That will generate a voltage to current ratio. For example, if I were to supply a known current to an element and measure the voltage that develops across the source, the ratio of the voltage to the known current would be the resistance of what we were testing. There is one catch. If we're using a ratio of the voltage to current to determine the resistance of a circuit, that circuit cannot be supplying any voltage or current of its own. That would mess up our measurements. So, to determine the resistance of a circuit, we have to start by turning off any independent sources. Remember that diamonds are forever, so we cannot turn off the dependent source. Beginning with the original circuit, the first thing we have to do is to turn off the independent voltage supply. 0 volts is guaranteed by replacing the voltage source with a wire. We can then apply a test source. I'm going to choose a 1 volt source. If we can then determine the current drawn from the 1 volt source, we can use the ratio of 1 volt to the test current to determine the equivalent resistance. I think this circuit will be most easily analyzed using node voltage analysis. I'll begin by selecting a reference node and define it as 0 volts. After identifying the other nodes in the circuit, we can assign them appropriate variables or values. After choosing directions for each of the currents, we can write a node equation at the yellow node. A second node equation can be written at the blue node. Now we have two equations with two unknowns. These equations can be simplified by multiplying through by 12 kiloohms. We can then gather terms. These equations are solved very easily by substitution. With the node voltages known, we can then write an equation for the test current in terms of the node voltages and solve for the test current. To determine the equivalent resistance, we just take 1 volt divided by the test current and we get 2,277 ohms, which, if you remember, is exactly what we got before. Now we should be able to handle anything. We have a method for determining the open circuit voltage directly, we have a method for determining the short circuit current directly, and we have a couple methods for determining the equivalent resistance of the circuit. For any particular circuit, all we ever need to determine using circuit analysis are two of these values. The third can be obtained by using Ohm's law. We also know the names of the equivalent circuits now. A voltage source in series with a resistor is the Thevenin equivalent representation, while a current source in parallel with a resistor is the Norton representation of the equivalent circuit. That's all for today. Go out and make it a great one.